Recall from part one of this lecture that we ended up with a table where we compared the pH values and percent ionizations of a strong acid, a weak base, and a strong base. In part two of this lecture, we want to look at additional examples of acids and bases, calculate their pH values and percent ionizations, to point out a few other things related to acid-base behavior. So we'll add to this table at the end of this part two of this lecture. So let's start with some additional examples. We'll look at a calculation of the pH of a strong base, and this time, instead of sodium hydroxide, we'll look at calcium hydroxide. Again, the concentration is 0.0351 molar. This is the concentration that we've chosen to use and compare acids and bases and their behaviors. Now, calcium hydroxide, like sodium hydroxide, is a strong base. We expect it to completely dissociate in water to the limit of its solubility, and we can describe the principal species in water using a balanced equation for the dissociation. We write the balanced equation here, and we remind ourselves that when calcium hydroxide dissociates, it produces one calcium ion and two hydroxides. The 2 in front of the hydroxide is going to be key here. If we think about what the principal species will be in solution, of course, since it goes completely to products or almost completely to products, there'd be almost no calcium hydroxide in solution in this form, and the concentration of calcium ion would be the initial concentration of the calcium hydroxide. But note the concentration of hydroxide is now twice that of the calcium concentration. And so a 0.0351 molar solution of the strong base calcium hydroxide is really 0.0351 molar calcium ion and 2 times 0.0351 molar or 0.0702 molar hydroxide, due to the fact that each calcium hydroxide produces one calcium ion but two hydroxide ions. So we can go ahead and calculate the pH of this solution. We'll first get the pOH, which turns out to be 1.15. We convert this to pH and get a pH of 12.85. Now let's try an additional example of a weak acid. Our job here is to calculate the pH of a 0.0351 molar solution of hypochlorous acid, HClO, whose Ka value is 3 times 10 to the minus 8. Before we show you this table of Ka values that I'm alluding to here, let me remind you that we're still using 0.0351 molar as our concentration, so we can compare to other weak acids and bases and strong acids and bases, all at the same concentration. Now on the right here is a typical format for finding the Ka value of a weak acid in a table of Ka values of weak acids. Right here, you'll notice that hypochlorous acid is listed. It gives the structural formula. It gives the conjugate base, OCl minus of hypochlorous acid, and most importantly for our purposes, it gives the Ka value. Probably pretty difficult for you to see there, but it's 3 times 10 to the minus 8. Since this is a weak acid, of course, it won't go completely to hydronium ion and the conjugate base ClO minus. So we set up an ice table, and since the initial concentration is still 0.0351, this should look very familiar. And so when we do the calculation, to find x, this looks very familiar from Lecture 1, x squared over 0.0351 minus x, only this time we're setting it equal to a Ka value that's much smaller than what we use for acetic acid, because hypochlorous acid is a weaker acid than acetic acid. Now if we solve for x, and again, this is doing way too much work here, we could just put this original equation into Wolfram alpha, and we find out that x is 0.000032435, taking some liberties with significant figures. And of course, the ICE table tells us that that is the concentration of hydronium ion at equilibrium, and would also be the concentration of hypochlorite ion. And so we state that here, hydronium ion and the hypochlorite ion are both have a concentration of 0.000032435 molar. Now the concentration of unionized hypochlorous acid would be 0.0351, the initial concentration, minus x, and we find that we get a number here that's hardly different than what we started with, which makes sense because hypochlorous acid is a very weak acid, so it's only going to ionize to a very small extent. So at equilibrium, pretty much all of the hypochlorous acid is in the form of the unionized form, although again, some hydronium ion has been formed. We can calculate the pH using that hydronium ion concentration, and it's 4.49. If we calculate a percent ionization, it's looking fairly ridiculously small, because again, this is a very weak acid, so hardly any of the hypochlorous acid ionizes to form hydronium ion and hypochlorite ion. And I'll remind you that I did take some liberties with significant figures here just to point out some things about the small percent ionization and about how hardly any HClO ionizes. I'm not sure if this writing is too small for you to read, but I want you to notice something, that in the table here, hypochlorous acid is written with its structural formula showing that hydrogen, the one that's lost as H plus to form hydronium ion, is actually originally attached to the oxygen atom of the hypochlorous acid. Now, interestingly, when we write just the formula, not the structural formula, we seem to write it in a way that implies HClO, that the hydrogen is attached to the chlorine. Well, the hydrogen is attached to the oxygen, so you might wonder why we write it as HClO when we're just writing the formula, and I make kind of a snide remark here that it's all part of a vast conspiracy to torture introductory chemistry students. Let's do another example of a weak acid calculation, and we want to once again look at hypochlorous acid, only you should notice that there is something different about this example, and that is that the starting concentration is now 10 times smaller than the starting concentrations we used in the other examples. Let's see what we get for a pH of this solution. We, of course, will use the same ICE table, only the initial concentration is 0.00351, again, 10 times smaller than what we used before. And we will, again, find an X value. And again, if we took a shortcut here and just put this original formula into Wolfram alpha, we'd find out that X turns out to be yet even smaller number than before, 0.0000102,466. And remember, that's equal to the concentration of hydronium ion, because that's how we've defined it in the ice table. So at equilibrium, the concentration of hydronium ion, which of course is equal to the concentration of hypochlorite ion, is equal to 0.0000102466 molar. And the concentration of the hypochlorous acid left is now even closer to the original amount. And if we calculate the pH, it's a little higher than before in our previous hypochlorous acid example, because we've used a more dilute solution of hypochlorous acid. It's now 4.99. Interestingly, the percent ionization, which of course we'd get by taking our value of X and dividing by the initial concentration of hypochlorous acid, is now 0.292%. Now that's still small, but it turns out it's actually larger than in our previous example. We'll get back to that. So let's make a final large table, and we'll take examples from part 1 of the lecture and part 2 and put them all together in a table. And this table is formatted a little bit differently than the previous one, but it'll be the same in the sense that we'll start with the strong acid on the bottom. So we had our strong acid HCl from part 1 of the lecture. Of course, its initial concentration was 0.0351. Does HCl have a Ka value? Yes, but it's ridiculously large because it really, at equilibrium, almost all of it goes to product. We calculated a pH of 1.45 and said it ionized about 100%. We then, in part 1 of the lecture, calculated the pH of a 0.0351 molar solution of the weak acid acetic acid. This did have a Ka value, which was small. And of course, now the pH is higher, still acidic. After all, it is a weak acid, but it's not nearly as acidic as HCl. And it ionized to the extent of only about 2.2%. It's a weak acid. Now in part 2, we added hypochlorous acid. When it had the same concentration as all the other acids, it of course has a very small Ka value, and its pH, yes, is still acidic, but it's higher than even acetic acid because it's a weaker acid than acetic acid, and it has an absurdly small percent ionization. We can stop here and just compare our two weak acids, and you can see we have two weak acids that have the same initial concentrations, but the weak acid with the larger Ka value, which would be acetic acid, shows a larger percent ionization and a lower pH. Now we can only make this comparison if we kept something constant, and here it was the initial concentrations of both, and the acid with the larger Ka will show a lower pH and a higher percent ionization. Now we also looked at hypochlorous acid at a concentration that's 10 times smaller than it was in our first example. Of course, we're still dealing with hypochlorous acid, so the Ka is the same, but the pH is now higher, still acidic, but it's not as acidic as the larger concentration of hypochlorous acid. That makes sense. Oddly, the percent ionization is higher than the larger concentration of hypochlorous acid. So we'll just remind you that when a weak acid is diluted, so if we take hypochlorous acid, 0.0351, that had a pH of 4.49 and a percent ionization of 0.0924, and we dilute it by a factor of 10, the pH goes up, it's less acidic because we diluted it. That makes sense. Oddly, the percent ionization, as measured by the percent of the original hypochlorous acids that ionize, is actually higher. So when a weak acid is diluted, the pH of the resulting solution increases, but so does the percent ionization. If you think about that a little bit, it seems odd, but it'll be important to remember going forward. Now we calculated the pH of the weak base. That was in part 1 of this lecture. Same concentration as the 3 on the bottom, 0.0351. It had a Kb value that was coincidentally the same as the acetic acid, but it is a weak base, so it gives a basic pH, and it ionizes to the extent of about 2.2%. The strong base NaOH, same initial concentration. Its Kb value is absurdly large because it's a strong base, has a very high pH. It undergoes about 100% dissociation. And finally, in this part, we added calcium hydroxide, same initial concentration, also an absurdly large Kb value. And the pH of this base is higher than of sodium hydroxide, but simply because it produces 2 hydroxides for every calcium hydroxide instead of the 1 hydroxide that's produced for every sodium hydroxide. And again, it ionizes or dissociates about 100%. Again, just to point out, calcium hydroxide produces 2 hydroxides per formula unit, so when initial concentrations are equal, which they are here, calcium hydroxide would produce a more basic solution than does sodium hydroxide. Again, the comparison is only completely fair if you have the same initial concentration. So one might ask, where is the cutoff between weak and strong acids and bases? We haven't given enough examples to show you that the Ka values of some weak acids could become larger and larger, and when do we call them very large and start to call them a strong acid, for example? Well, here's a scenario you might want to think about. Suppose you were teaching a PE class full of healthy 18-year-olds that had no physical limitations. You decide to test their strength by seeing how much each student could deadlift. Not surprisingly, you find a range of results. Some students can only deadlift 10 to 20 pounds, while others can deadlift as much as 400 to 500 pounds. It's obvious to you that you have some very weak students and some very strong students. If you were then asked to arrange the students into categories, you would have to decide where your cutoffs would be between very weak, weak, strong, very strong. Now in chemistry, Ka values for acids and Kb values for bases come in a wide range of values. Some are so large, we just say very large and call the acids or bases very strong, like we did here. Ka very large, strong acid. Kb very large, strong base. Now some are so absurdly weak that we can barely even call them acids or bases. There is a whole range of values in between those limits, and we are left with phrases such as a fairly strong weak acid to describe an acid that's in general in the weak category, but whose Ka value is large compared to most weak acids.